Hello, I'm Daniel and I'm going to talk about our project. The first step of our project, other than remotely control the Pioneer, was to map the environment, in this case, the North Tower 5th floor. To do that, it was used a ROS package called G-mapping. The G-mapping package is used to provide a laser-based SLAM, which is a technique used by autonomous robots to generate a map from an unknown environment. The G-mapping package will create an occupancy grid map based on the data from the laser and the robot's pulse from the odometry. Usually the odometry generates several errors, and to face these issues, the G-mapping package uses a raw black-hole-ized particle filter, which is a very efficient filter. In this clip we were controlling the robot remotely in order to do the map that will be used by the robot in localization. After completing the map, we needed to localize our robots, and therefore we used the MCL. The MCL is a probabilistic localization algorithm for a robot's 2D movements. This system uses the Monte Carlo localization approach, which uses a particle filter to track the robot's pose against a known map. The algorithm receives the information from a map server, readings from the lasers and odometry, and the output will be an estimation of the position. In the beginning, when normally there is no information about the robot's position, it is possible to give the algorithm an estimation about the position, and that will make the particle convergence faster. In this model, we tested with all particles evenly distributed and the algorithm converged. Noticing that when we don't know where we are, the algorithm adapts and it generates a lot of particles, which is computationally expensive. In the beginning we had a lot of challenges with the navigation. In this clip you can see our robot struggling to pass. In this case, we needed to tune down the footprint of the robots by specifying his dimensions. The navigation was implementing using the ROS navigation stack, which requires the configuration of some parameters in order to obtain good results. The move base is compatible with the maps created by the G-mapping, and so it was used the grid maps created during the mapping process. Based on all this, we fine-tuned cost maps to better plan the path between 2 points on a map. Through the move-based package, the robot is capable of navigating between 2 points, and thanks to the data from the lasers, it is capable of detecting objects on its path, allowing the robot to avoid them and still continue safely to its destination. It is important to know the robot's position at every step of its navigation, so the generated speed commands are reasonable. This is the reason why MCL was used instead of just odometry data. The accumulation of errors of the odometry would make this method unreliable. One major aspect of the navigation was the fine-tuning of cost maps that would allow a flawless navigation by adjusting parameters like the footprint of the robot, the ray trace parameters, amongst many others. A lot of tests were made and some videos are presented here. The Kinect is a group of two different cameras with different functions. In our project, only the second one, the depth camera, was used because we did not need any information about the color and brightness of the objects in order to detect body positions. To facilitate the integration with the project, we would use the OpenE library through the OpenE Launch and the OpenE Tracker packages. The OpenE Launch is responsible for establishing the connection between the Kinect and the computer, loading all the necessary nodes and converting the pictures captured by the Kinects into a format that could be read by ROS packages. The OpenE Tracker allowed us, using the depth image received by the OpenE Launch, to detect and follow people. Whenever a person stands in front of the camera, it can distinguish the head, the shoulders, hands, elbows, knees, wrists, and feet, giving to each of it a set of TF coordinates. Those coordinates are based on the camera main focus, and once it has access to several sets of coordinates, it is possible to identify different gestures made by someone in front of the camera. In this clip, we can see a simple example of application of our integrated project. We start around the graphical user interface. The robot grabs a bottle, the Kinect user asks for gesture calibration, and our robot proceeds to travel to the delivery point, where he drops the bottle. Noticing the map on the upper left corner is a topological map used by our robots. With this map, he identifies rooms by a label and isn't just following coordinates. At the end, we show a voice feedback example. Thank you for watching.